Hey, good morning, everyone. So today we're just going to be briefly reviewing arc length. Let's see, indefinite integrals, and then if that's okay, I want to go over some test review, just sort of broadly. Okay, cool. So just to do this quickly. Actually, that's not necessary. Right, so one of the main things we learned this week was the formula for the arc length of a given function, right? If any function is continuous on some interval a to b, then its arc length is always defined as integral from a to b, square root 1 plus f prime squared. And so we can derive that later if you want, but I think it'd be good to just hop into examples for now. So let's say we want to find let's say we want arc length of y is equal to natural log secant of x from 0 to pi over 4. So if we were to start this one out, the first thing we have to do is find what f prime is going to be. So if y is equal to natural log secant of x, what is its derivative going to equal?
1 over secant x?
Okay, well,
Oh, no.
1 over secant x, right? That's the derivative of the outside. What's the derivative of the inside?
Secant x times tangent x.
Right, times secant x, tangent x. And if we do, simple cancellation, that leaves us with tangent of x. So, therefore, our arc length is going to be integral from 0 to pi over 4, our boundary, 1 plus y prime tangent squared. Right, and from here, who can simplify the inside of this root? Right, 1 plus tangent squared equals what? Secant squared. And then square root of secant squared of x. And this is a good test review. Who remembers the integral of secant?
That's natural log of secant plus tan.
Right. Natural log of secant of x plus tangent of x. And then finally we plug in, so we have natural log of secant pi over 4 plus tangent pi over 4 minus natural log of secant 0 tan 0. So what's secant of pi over 4? If you're ever not sure, it's just the reciprocal of cosine pi over 4.
2 over 2.
Right. So yeah, cosine is normally root 2 over 2, so you just flip it. 2 root 2. What's tangent of pi over 4? 1 minus natural log of, so cosine of 0 is normally 1. So if you take its reciprocal for secant, it's still 1. 0. Let's see, 2 divided by root 2 is just root 2. That's 1. And then what's natural log of 1? 0. So our final answer will just be this right here. Natural log root 2 plus 1. And we'd say that this value represents like the absolute length of the arc. You know, if we imagine this function, natural log of secant, Is that an asymptote? It's not a particularly simple function to draw, but the important idea is from x equals, let's see, 0 to pi over 4. The length of that curve over the interval, that should equal natural log root 2 plus 1. Very cool, makes sense? Can I go to the next page? Actually, I could probably just scroll. No, pages. Continued, and just for a slightly harder example, let's say we wanted to sample arc length of, let's see, I had y equal okay, the arc length of this polynomial from -1 to 1. So just as before, first thing we do is we find the derivative of our original function. So what's the derivative of this polynomial? It'll be, yeah, x plus 1. So then we have our integral, or the arc length is going to be integral from -1 to 1, square root 1 plus f prime squared. Okay, and how do we go about it from here? I'm not sure if you could, but if you, even if it did work out, I think that would still be a longer way to get the same answer. I think what actually might be better is we can say, let x plus 1 equal tangent of theta. Then what's the derivative of x plus 1 equal to? Right, well, yeah, dx, right. And what's the derivative of tangent? secant squared. That's the derivative of secant. D theta. So we have that our integral becomes, let's see, square root 1 plus, that whole thing is tangent, so tangent squared. Let's see, and then dx becomes this, secant squared theta, d theta. And just as we said before, 1 plus tangent squared gives us secant squared. Square root of that is secant times. And I thought this one would be a good review because it kind of leans into like a harder trig problem that you guys have reviewed before. Does anyone know how to solve a trig integral like this where it's just secant some odd power? Right, how do we split it apart?
Take out secant.
Okay, and then
You add secant squared theta.
yeah,
And
Speak up.
integration by parts.
well, let's see. So then what would be u and what would be dv? Of these two, which has an easier integral to do?
Secant squared of theta?
Secant squared, right? Theta, because what's that integral?
Tangent.
Tangent. So that means that has to be secant of theta, and then its derivative has to be, should give myself more room. Right, secant tangent. So altogether, that leaves us with uv minus integral of what? V du. And let's see, that. Secant squared tangent. I might be wrong, but I don't think there's a good path forward on this one. Yeah.
Wouldn't it be better to make secant squared theta into 1 plus tangent squared?
That was my
theta?
original thought. I wanted to see if this worked out too, but that seems like it gets to a very easy answer, so apologize for that. So let's say instead we format it like this. This integral becomes secant of theta times 1 plus tangent squared theta, d theta. So that means we're left with integral secant theta plus secant. Oh, I guess I kind of jumped the gun, didn't I? Because this, looking at it again, this should actually work out. Okay, I'm sorry. So let's say we do integration by parts. Again, ignore that. That actually would have been fine. If we do integration by parts like this, let this thing be dv and let this thing be u. So dv is secant tangent, and then u is just tangent. So what's the integral of secant tangent? Is what? Secant. And then what's the derivative of tangent? Right, secant squared theta. So we have that original integral, secant cubed theta d theta, has to equal, let's see, that, so secant theta plus, and then this whole integral becomes uv Oh, do something wrong?
Secant cube theta. Oh, wait,
What should be secant cubed?
no, no.
Okay, it's good. Okay, cool. Right, uv minus integral of v du. Right, and who remembers the trick for doing this from here? Right, we've recreated the original term on this side, right, secant cubed. We can just add this to both sides. Plus integral secant cubed theta plus integral secant cubed theta, which would mean this and this cancel, and this sum up to, right, 2 of them, so 2 times that. And it equals what's remaining. Integral of secant plus secant theta, tan theta. And so finally, you know, I can divide both sides by 2, and I get, you know, integral secant cubed is equal to 1/2. Now, what's the integral of secant all by itself? Right. And then plus. And then the very final step is, remember, our original substitution was what? X plus 1 equals tangent of theta. So do we remember the trick for how to solve that in terms of secant? Or rather, how to find a substitution for secant now that it's in our final answer?
We create a triangle.
Exactly. So, and the logic is, for a right triangle, tangent's thought to be equal to what? Opposite over adjacent. But in our case, tangent's also equal to x plus 1, right? So therefore we can label x plus 1 as opposite of this hypothetical triangle and 1 as adjacent. So 1, 1, and then by Pythagorean theorem that would have to be this squared plus 1 squared, which is 1. Okay, so what is secant in terms of triangle side lengths.
Hypotenuse over adjacent.
Right. It's the flip of cosine. And in our triangle, that corresponds to, let's see, hypotenuse. So square root x plus 1 squared plus 1 over adjacent, which is 1. And so now finally, we can plug in for our original answers, or the trig subs we have. So every secant will become square root x plus 1 squared plus 1. And it's a plus tangent, which is x plus 1 plus secant times tangent. So secant times tangent. Is our final answer. Oh, plus c.
We would evaluate too, right?
Thank you. Right, we did. I feel like so long ago. There were bounds, right, from -1 to 1. Okay, so my apologies. The last step will be all this, plug in 1. So we've got natural log of, let's see, square root 1 plus 1 is 2 squared plus 1. Let's see. Plus x plus 1. Plus, it'll still be square root that times 2, and then minus 1/2. Natural log, where we plug in -1. Okay, good. So that should be our answer for arc length. Okay, any questions on that one, or? Make sense? Okay, cool. So if I can move to the next page. Right, the last new thing we're going to cover is just briefly go over proper integrals, which is just, it's just right, indefinite integral, it's just any integral that whose bounds aren't, we consider like properly defined. And what that can mean is either the bound is not a number, so it's an infinity, or the bound is going over somewhere where the function has a discontinuity. And we call those type 1 and type 2 respectively. And so, for example, okay, let's say we want to do this integral. 0 to infinity x e to the negative x squared dx. The way we deal with this, having, in the case of type 1, having an infinity in the boundary, is that instead of writing this infinity right here, we just replace it with a variable whose limit is going to infinity. And it can be any variable, it just can't be the same one as that variable. Okay. And does anyone know how we'd solve this integral?
Use substitution.
Right. It's a good choice. Where u should equal what?
Negative x squared.
Good. So therefore, du should be what? Negative 2x dx. Well, and then, if we arrange this a bit even, we have dx is negative 1 over 2x times du. Okay, so that should give us, let's see, our integral will become what? X e to the u, and then dx becomes all this, negative 1 over 2x du. And we can see, x and x will cancel, and we're left with -1/2 e to the u, what's the integral of that?
So you,
Right, it'll be itself, essentially, -1/2. Right, limit e to, or -1/2 e to the u. Which, finally plugging back in, that'll be -1/2 e to the -x squared. Okay, so far so good. And the final part is we just plug in and we take the limit of that result. So in our case, if I plug in, I get, let's see, the first term will be -1/2 e to the -t squared minus -1/2 e to the 0. Sorry, I don't know why I wrote 0 right there. T is going to infinity. Okay, and as t goes to infinity, does everyone know what e to the -t squared would head towards? 0, right? Does that make intuitive sense for you guys? So be -1/2. Like you said, that limit is 0. So this times 0 plus 1/2 times 1. Oh, sorry, yeah?
could you explain why it is 0 for the limit?
Oh, sure. So let's make it on the side a bit. We're taking limit as t is heading towards infinity in the positive direction, e to the -t squared. It might help off the bat if we rewrite this, e to the -t squared, as a fraction. So I can always take a negative power and put this to the bottom.
Gotcha.
Right, and does kind of clarify things. As t goes to,
Because then the denominator's just getting bigger and bigger, so I think it's getting closer.
Right, the whole fraction would therefore head towards 0.
I got it.
Okay, cool.
Yeah.
Yeah. Okay, and just one last example from this one. Let's do integral from 0 to 3, 1 over x minus 3. So these are ones we kind of have to be careful about, because if we're just looking at it, it might not be immediately obvious that it's improper in the same way this one is. But if we think about where this function is discontinuous, right, does it have any discontinuities on our boundary? At 3 itself, right? So this will qualify as what we call a type 2 improper integral. It's improper because one of its bounds is, a discontinuity. And so before we used a limit statement to correct that, we're going to do the same thing here, except now our variable is heading to 3. Wait, I still wrote 3. It's D. We'll say for type 2s, it is also important to consider which side, left to right limit, t is approaching the boundary from. So in this case, do you guys know which side, like positive or negative, t would be approaching 3 from? Right, because that's where the boundary is, right? So you have to approach from, the negative side. Not always relevant, but sometimes. Okay, cool. So, and does anyone know the integral of this guy off the bat?
The natural log of x minus 3.
Right, you could do a u sub to show it, but it's pretty simple integral. So we have limit t going to 3 from the left of natural log x minus 3, 0 to t. Which will equal right, plug in the top bound, plug in the bottom bound. And because these are absolute values, that's just becomes t to the positive 3, or ln of positive 3. Okay, so the last sticking point is we need to do this limit right here. Natural log of t minus 3 as t approaches 3 from the left. So let's see. So if we imagine some values of t approaching, 3 from the left, are those going to be numbers that are bigger or smaller than t if you're coming from the left side? Smaller, right, slightly. So let's say t was something like, therefore, let t equal, just to get an idea of what's happening. It's like 2.9, and we have natural log of, let's see, this minus this is negative 0.1, and then absolute value, so 0.1. And we can say let t equal 2.99. Then we have natural log of, again, 0.01. So as t gets closer and closer to 3 from the left side, we see that the inside of natural logs is getting closer to 0 from the right side. Does that make sense? Because these are all numbers that are slightly larger than 0. And so if we look at the graph of that, actually, let's keep it red. The graph of natural log looks something like that. So what's the limit of it as x goes to 0 from the right side? If x is slowly coming from here. That limit's heading towards negative, it's heading straight down, it's heading towards negative infinity. So we get this as negative infinity minus natural log of 3, which means our answer doesn't exist, it's divergent. It's a non-number answer.
So anytime we have infinity on our answer, it's done.
It's divergent, yeah. And that's really the dividing line. If it's equal to a number, it's always convergent. If it's equal to infinity or negative infinity, divergent. Okay, any questions on this problem? Did the last part make sense with the, sort of like thinking about t as it approaches -3? That's probably like the least intuitive part of doing these, but did that come across? Did anyone feel like that didn't really make sense or they couldn't replicate it? Feeling good? Okay, cool.